Okay, this is problem number 4 on fatigue or design against fatigue. So it says here in the figure below the leaf spring. So we have a leaf spring here. It is modeled as a cantilever beam. The leaf spring is straight and unstressed when the cam and the shaft are removed. You see this line here, horizontal line. Just imagine this cam and shaft have been removed. So the spring here, because of the elasticity of the spring, is going to be almost flat here in this case. The material of the spring is called drawn annealed chromium molybdenum steel. So the material from which this spring is made is given with coated tensile and yield strength as 115,000 pound/inch squared. This is the ultimate tensile strength. And 98,000 pound force/inch squared. This is the yield strength of the material, and as you see here, it is given in imperial units. The stress concentration at the support may be neglected, so we're going to consider here that K sub F is equal to 1. Assume that the endurance strength is equal to 0.5 multiplied by S ultimate for steel material, and the elastic modulus of the material is given as 30 multiplied by 10 to the power 6 pound force/inch squared. If the cam rotates continuously, find and comment on the factor of safety for the spring. So we want to find the factor of safety of this spring based on this design and this material. Note that the deflection of the cantilever beam is given by this equation. So we have a cantilever beam, and then this is how to calculate the deflection. So delta, which is the deflection, is equal to W, which is the force, because we consider here that we have a point force or a concentrated force at this point, multiplied by the length of the cantilever beam between the point of the application of force till the fixed part here, or the fixed side, divided by 3, multiplied by the elastic modulus of the material for the spring, times the moment of area, second moment of area of the material or the geometry of this spring. So based on the geometry here, see, we have this length as 10 inch, right? Then we have the width of this spring as 1 inch, the thickness as 0.125 inch, and then we have two settings here. The first gives us the minimum deflection of the spring, where the distance between here, this is the unstressed, undeflected settings, and this point here, or at this, when the cam and the shaft in this position. So the distance here, the deflection here, is the radius of this circle, which is 0.5 inch. So the minimum here deflection is going to be 0.5 inch. But just imagine if this cam rotates 180 degrees, so this step here is going to push this spring further down, and then the distance between this unstressed location or position to the tip here is 1 inch. So the maximum deflection is 1 inch in this case. So the width is of the spring is 1 inch, the length is 10 inch, the thickness is 0.125 inch. The elasticity is given, yield strength is given, ultimate tensile strength is given, and this assumption for the steel material, the endurance strength is equal to 1/2 of the ultimate tensile strength, and also the equation to calculate the deflection is given. So based on the configuration, you see that the minimum or the normal deflection is 0.5 inch, which is the radius of the shaft. The maximum deflection when the top tip of the cam pushes this spring further down, so the maximum deflection becomes 1 inch. So we have two settings now, and based on these two deflections, we can calculate the forces, actually the minimum force and the maximum force. The second moment of area depends on the geometry or the cross-sectional area of the spring. The cross-sectional area of the spring is rectangle, so the width is B and the thickness is D. So the second moment of area in this case is P multiplied by this perpendicular dimension cubed over 12. So the width is 1 inch, the thickness is 0.125 cubed divided by 12, and this gives us the second moment of area for the spring cross-sectional area. Then here we can rearrange the equation for the deflection in order to find the force, the minimum force and the maximum force. Remember, from here we have two deflections. So the first one is 0.5 inch. So if we substitute this value into here, so the minimum value or the normal value of the deflection is 0.5 multiplied by 3, which is constant, multiplied by the elastic modulus of the material of the spring, 30 times 10 to the power 6, times the second moment of area, which is being calculated here, divided by the length, which is, if you remember, 10 inch cubed. This gives us the minimum force of the spring, or the minimum force applied on the spring based on the rotation of this camshaft system. But here you see the maximum deflection is twice the minimum or the normal deflection. And here in this equation, the length is the same, elastic modulus is the same, the cross-sectional area and consequently I value is the same. So the only thing that changes is the delta value. So if we double the delta value here, so the force doubles. This means that the maximum force is twice the minimum force. And also, if I go back here, you see, just imagine you have a force here and you want to calculate the maximum bending moment. So the maximum bending moment is going to be here at the support. So the force multiplied by the distance gives you the bending moment here. So you have to multiply the minimum force by 10 and the maximum force by 10 to find the maximum and the minimum bending moments. And this is what happens. Take this value, multiply by 10 inch, it gives you the minimum bending moment. Take this value, multiply by 10 inch, it gives you the maximum bending moment. So now we have the minimum and the maximum bending moments. And based on that, we can calculate the mean and the reversed bending moments. So the mean bending moment is the maximum plus the minimum over 2. Now we know the maximum bending moment value, the minimum bending moment value. So it means that the mean value of the bending moment here is 109.89 pound force times inch. And the reversed bending moment here is the maximum value of the bending moment minus the minimum value over 2, which is 36.63 pound force inch. And if we use the Soderberg equation, so in this case, we are asked to calculate the factor of safety of the spring based on the given material and geometry. So the yield strength of the material was given as 98 times 10 to the power 3 pound force inch squared multiplied by I over Y. So because we have a rectangular cross section here, so the Y value is going to equal the thickness of the spring over 2. So the thickness of the spring is 0.125 over 2. This is the Y value. So Y value is equal to the thickness over 2. The second moment of area was calculated before. It's 1.628 times 10 to the power negative 4 inch to the power 4. The mean value of the bending moment was calculated based on this equation. It's 109.89, and the fatigue stress concentration factor is considered as 1 here because it says ignore this value. The yield strength of the material is 89, and here the value of the endurance strength is equal to 0.5 times the ultimate tensile strength. So if this is the ultimate tensile strength and then multiply this value by 0.5 means that we just multiply here by 2. This is the same answer. then we are going to multiply by the reversed value of the bending moment, which is 36.63. This eventually gives us a factor of safety of 1.48. As based on the learning pack. So this, if the factor of safety is greater than 1, it means that this component under the loading conditions and using this material and geometry is going to last forever. Or